spontaneously, as long as they can make the universe stupider quicker. In other words, the entropy of the universe will increase. The universe will become more disorganized as long as the collection of molecules becomes more organized. So this is a driving force for life, it turns out. And here we see another example of the same kind of a phenomena. So here we're looking at a chemical gradient. We have what's known as a redox reaction. And that's basically what we are. We take in what's known as reduced carbon, hydrocarbons. Just like you burn gasoline in your car, we burn carbohydrates and fats, which are hydrocarbons. They have energy in them and you can burn them. And that's what we do, and we do it in a controlled manner. That controlled manner being our metabolism. And we ultimately wind up taking electrons that are forced onto carbon, ultimately via the sunlight, photosynthesis in the plants, and we allow them to step down gradually and release their energy, which we capture to maintain the organization which is characteristic of life. So health is how efficiently we do that. And disease is when we start to do that inefficiently. And ultimately, death is the return to equilibrium. So we require the constant flow of energy into us so that we can extract order out of it and use that order to maintain us in our organized fashion. And as we age, we lose that capacity more and more, and we'll go into that in a little bit more detail. So here what we see is another Petri dish, and in this Petri dish we see all these organized patterns emerging from the chemical gradient dissipating its energy, essentially. Just the way the heat flowed from the bottom to the top of the Petri dish and created those patterns, here we're seeing the flow of electrons creating patterns. And there's an indicator that gives you colors, and that's what you're seeing here. So again, highly improbable events, impossible events by conventional thinking that occur reproducibly and that involve cooperation of molecules. All right, so this is the Zhabotinsky reaction. Here I have a little test tube demonstration that I do. So I start off by shaking it up very thoroughly so we all agree that all the molecules are random. And what you're going to see is a blue color emerging from the bottom and traveling up. And that's the indicator dye. But it's telling you that something different is in the bottom of the tube and then moving up, that there's molecules that have organized themselves, and it disappears. And it's going to come back again, and it's going to repeat itself. So this brings up two key concepts to this thermodynamics, far from equilibrium thermodynamics, that you can have structures in time and space. And this is very key because we are all composed of oscillations, as you just saw in the past, in terms of tumor necrosis factor levels going up and down, and inflammation going up and down, and arthritis. Those are just some examples. There are many, many examples. You know, we breathe with periodicity, our heartbeats occurring with periodicity. We have EKGs, we have menstrual cycles, sleep cycles. So cycles are an intrinsic property of living systems, and we'll see how that is an emergent phenomena from the underlying physics when we have essentially charged batteries. All right, so distributive structures are fundamental to life. They are the basis of far from equilibrium thermodynamics that defines health and disease and life and death. And what we're looking at here are examples of critical compounds that are metabolic intermediates. In other words, part of that process of how we take reduced hydrocarbons and burn them so that we can have energy to exist and to live and to be healthy and to do the things of life. These are compounds that are part of that process, and we see that they're oscillating as well. Some of them in phase, some of them out of phase with respect to one another, but nevertheless we see oscillations. So this is a key component of where I want to take us. And it turns out that this is something known as a limit cycle, that oscillations occur within a range, and that we can have, that the systems themselves will maintain what that range is. So what we're seeing here is that products and substrates, things that interact with one another. It could be, for example, the production of tumor necrosis factor, and it could be what created it, or it could be what turns it off, that would fit into this kind of a category. And we see that we could start at this position, and it'll go and it'll settle down in that dark area, or we could start within that area, in other words, the ratio of substrates to products, and it'll go back out to that same area. So there's an area of dynamic balance. And this is true within our organs, within our cells, within us, on all levels. This is true. And it turns out that the system, the molecules, they maintain this balance level by virtue of these intrinsic properties of life, this creative nature that emerges when we have far from equilibrium situations. So it may be that this limit cycle, where things are settling in, are in this position if we were looking at a particular, say, biochemical event for one of us, and it may exist in some other area for someone else, and another area for someone else. And it may be that this represents health for us, and maybe we shift to another area when we become unhealthy, when some damage or imbalance has been placed upon a biochemical system that shifts the system. And what we'd like to do is to restore it back to its balance area. So biochemical imbalances lead to excess free radical production. And we see that what we're looking at here really is the concept of yin and yang, antioxidants, pro-oxidants, anti-inflammatory and pro-inflammatory. These are the balancing acts that are creating whatever the balance is that's characteristic of every one of us. Different. We're all different. We're all the same, and we're all different at the same time. So that's why not every medicine is great for everyone, and that's why we have to see what works for an individual. Cannabis can be great for an individual under certain circumstances, and it could kill you under another set of circumstances. So it's a matter of learning what's good and when it's good and using it appropriately, which requires knowledge. And that's all we're trying to do here. So hypothesis that, and this is a fairly generally accepted hypothesis, this first part here, that free radicals are the friction of life. That the longer we live, the more we make these free radicals. Free radicals are highly reactive compounds. They react with things, including our DNA. They can be mutagenic, which then changes our DNA, and they can lead to a whole variety of age-related diseases. Well, it turns out that the endocannabinoids are the oil of life. And what they do is they minimize, it's friction. We're talking about biochemical friction, essentially. And what we'd like to do is minimize the consequences. We don't want ourselves wearing out. So we need to oil ourselves appropriately. And our bodies try to do that, but there's a direction to our imbalance. Because even though we're all unique and we're all different, we all share a certain characteristic. We're all getting older. And that age is attributable to the accumulated damages that are occurring from that friction. And we'll elaborate on that a little more because, as was pointed out by Dr. Mechelem, these things have constructive roles as well. They're part of signaling mechanisms. So free radicals act as chemical messengers. If something's wrong, they allow us to realize there's an imbalance. And when I say us, I mean at our chemical level, within ourselves, between our organs, and between us as individuals and in formations within our societies. How do we fix things? But certainly on a chemical level, free radicals tell us that something's wrong, let's try to fix it. But alternatively, they say something's wrong, let's kill it. Because we don't want, for example, genetically damaged cells in us. If we can't fix those genetically damaged cells, and we have mechanisms to do that, DNA repair mechanisms, then we want to get rid of those cells because those are the cells that go on to be cancer. So I'm going to give you an example now. What I want to try and do is show you that these physical properties that I'm describing, these flow-dependent dissipative structures as they're known, are truly realities within biological systems. And we're going to use, as an example here, neutrophils, which are components of your immune system. These are the foot soldiers, so to speak, of your immune system. You get a cut, these are the first things that go there, and they try to sanitize the area. And how do they sanitize the area? By making free radicals, because they're going to use free radicals to kill pathogens that might be invading you. And interestingly, free radicals are also a consequence of radiation. Aside from the heat and the blast of a nuclear weapon, the radiation results in free radical production, and there are severe biological consequences. So here we're seeing how the body has learned to use that. We start off with some oxygen. We have one of these biochemical intermediates that has hydrogens on it here. And we wind up producing free radicals known as superoxide.